Somewhere in the imagination of a physicist, there is a cat. It is neither alive nor dead. Its fur is both warm with breath and cold with stillness. And until we lift the lid of its box, we will never know which is true or if both are true at once. This isn't a ghost story. It's not even a story about a real cat. It's about an idea. One that has lived for nearly a century and has haunted scientists, philosophers, and dreamers alike. An idea so strange, so delicate, that it blurs the line between what is and what might be. Welcome to The Sleep Scientist. If you enjoy deep late-night journeys into the mysteries of the universe, explained slowly, calmly, and with wonder, you're in the right place. Make yourself comfortable, maybe dim the lights, and let us wander into the quiet strangeness of a cat that forever changed the way we understand reality. And if you'd like to join me on more of these nighttime explorations, do consider subscribing. Erwin Schrödinger did not own this cat. In fact, no one has. It exists only in the realm of thought, conjured in 1935 as part of a daring mental experiment. At first glance, it sounds like a riddle. It's the kind you might tell to confuse a friend. Imagine a cat that is both alive and dead at the same time. But Schrödinger wasn't joking. He was making a point. And that point would slice deep into the very foundations of physics. Before this cat, physics was split in two worlds. The classical world, the one of apples falling from trees, planets circling the sun, and predictable cause and effect. In the quantum world, the hidden, subatomic realm where particles behaved in ways that seemed impossible. The two worlds barely spoke the same language, and Schrödinger's cat was about to make that gap impossible to ignore. Picture it with me, a sealed box. You cannot see inside, cannot hear, smell, or touch what's within. All you know is that there is a cat inside and a device connected to something dangerous. That something is a tiny bit of radioactive material. So tiny, in fact, that there's only a 50% chance it will decay within the next hour. If it does decay, it triggers a mechanism that releases poison, killing the cat. If it doesn't, the cat lives. Simple, right? You're either alive or dead. Except in the strange language of quantum mechanics, that's not how the story goes. In the quantum world, until we check, the radioactive atom is in a state called superposition decayed and not decayed at the same time. And because the cat's life depends on that atom, the cat becomes linked to it, live and dead, simultaneously. Not in some blurry metaphorical sense, the mathematics of quantum mechanics. It is both. It's a strange image, a living thing trapped between life and death. Our minds recoil. We want the comfort of one outcome or the other. But Schrödinger's cat is a bridge between worlds. The sharp, solid certainty we experience every day, and the soft, ghostly probabilities that rule the tiny scales of atoms. And here's where the unease begins. Because if quantum rules apply to atoms and we are made of atoms, shouldn't they apply to us too? Schrödinger designed his cat to force that question. If quantum physics is truly true, then why do we not see these strange both-at-once states in our daily lives? Where is the line between quantum and classical? Or is that line an illusion? To understand the depth of this paradox, you have to step back to the year it was born. The mid-1930s were a golden and chaotic time for physics. Einstein had already shaken the world with relativity. Planck had cracked open the first hints of the quantum with his idea of energy quanta. Bohr and Heisenberg had developed the Copenhagen interpretation, which said that particles existed in all possible states until observed. And that's what Schrödinger didn't like. The idea that reality only became real when someone looked at it felt absurd. So he imagined something even more absurd, a cat whose life depended on it. In doing so, he turned an abstract puzzle about particles into something uncomfortably close to home. And that's why it stuck, because this wasn't about electrons anymore. This was about life, death, and the very nature of reality itself. There's something haunting about imagining that moment, the one before you open the box. Your hand hovers above the lid. Inside, a quiet universe exists. The cat is there. It is alive. It is dead. It is neither. It is both. Time seems to hold its breath. Your choice to look or not to look feels suddenly important. Oh, yes. In that moment, you hold reality itself in suspension. And perhaps that's why Schrödinger's cat has lived in our imaginations for so long. It is more than a physics problem. It's a mirror, reflecting our own unease with uncertainty. We start our journey with this cat because it sits at the crossroads of everything strange about quantum mechanics. It will lead us into superposition, entanglement, the observer problem, and even the possibility of infinite parallel universes. It will also lead us into deeper, quieter questions. Is reality something we discover or something we create? Do things exist before we notice them? And if they don't, what does that say about the universe? And us tonight, we open the box slowly. Not to save the cat, not to harm it, but to understand what it means for something to exist in more than one way at once. The lid is still closed. The cat waits. And so do we. The lid of the box remains closed. The cat waits in its quiet twilight between life and death. But to truly understand how such a creature could exist, even as a thought, we have to step back in time. To a world before the quantum existed in anyone's mind. It begins not with a cat, but with a furnace glowing in the dark. At the turn of the 20th century, physics felt nearly complete. Newton's laws had explained the motions of planets and the fall of apples. Maxwell's equations had tamed electricity and magnetism into predictable patterns. The machinery of the cosmos seemed solid, reliable, and complete. Lord Kelvin, a leading physicist of the era, even declared that there were only 2 small clouds left to clear up in physics. One of those clouds was a puzzle about light. Imagine heating a metal plate until it glows first red, then orange, then white. Physicists thought they understood why it changed color with temperature. But when they calculated the spectrum of light it should emit, something went horribly wrong. Their equations predicted an infinite amount of energy at short wavelengths, an absurd result known as the ultraviolet catastrophe. In theory, that glowing metal should blast the universe apart with infinite ultraviolet light. It didn't, and the equations were wrong. In 1900, a quiet German physicist named Max Planck decided to solve the problem. To do so, he had to take an unthinkable step. He suggested that energy wasn't continuous like a smooth wave, but came in tiny, indivisible packets. He called them quanta. The word felt strange in the mouth, but the mathematics worked. By assuming light could only be emitted in these small packets, Planck's formula fit reality perfectly. Planck himself didn't fully believe it was a physical truth. He thought it was just a clever trick to make the math behave. But the seed had been planted. And seeds have a way of growing beyond what their planter imagines. 5 years later, in 1905, Albert Einstein took Planck's quanta seriously. He used them to explain the photoelectric effect, a phenomenon where shining light on metal can eject electrons from it. Classical physics said any color of light, if bright enough, should eventually knock electrons loose. Experiments showed that only light above a certain frequency could do it, no matter how dim, and that brighter light below the threshold did nothing. Einstein's explanation was bold. Light itself comes in discrete particles, photons, each carrying a specific amount of energy. If a photon didn't have enough energy, no electron would budge. This was the first time someone truly embraced the idea that the universe, at its smallest scales, worked in a way utterly unlike our everyday experience. Planck and Einstein had cracked the first hints of the quantum, but they hadn't yet disturbed the larger structure of physics. That came in the 1910s and 1920s. When experiments with atoms began to reveal something deeply unsettling, electrons didn't orbit atoms like tiny planets, as Bohr's early model had suggested. They behaved as if they were both particles and waves. Sometimes they appeared in one place. Other times they seemed to be spread out in space like a ripple on a pond. The solid predictability of Newton's universe began to melt. The famous double-slit experiment showed just how strange things could be. Shine light through 2 narrow slits, and you see an interference pattern, as if the light is a wave, rippling and overlapping. But if you dim the light so that photons pass through one at a time, the pattern still emerges, as if each photon is interfering with itself. Even more bewildering, the same is true for particles like electrons. Fire them one by one through 2 slits, and they behave like waves. Observe them closely, and they suddenly behave like particles again. It was as if the universe itself changed its mind depending on whether you were looking. Faced with this, a group of physicists, led by Niels Bohr and Werner Heisenberg, crafted what became known as the Copenhagen interpretation. Its key idea was radical. A quantum system doesn't have definite properties until it's measured. Until then, it exists in a superposition of all possible states. For an electron, that might mean being in multiple locations at once. For a photon, traveling as both a wave and a particle, until an observer forces it into one reality. This was not an easy pill to swallow, it implied that reality itself was not fixed, but fluid, and that observation was what crystallized it. Some embraced the Copenhagen view. Others, like Einstein, found it intolerable. Einstein famously said, "God does not play dice with the universe." He believed there must be hidden rules, unseen variables that made reality definite even when unobserved. Schrödinger himself also disliked the Copenhagen interpretation. He thought it was incomplete, even absurd. When to prove his point, in 1935 he devised the most unsettling scenario he could imagine. A cat sealed in a box, whose life or death depended on a quantum event. If Copenhagen was right, the cat would exist in a superposition, alive and dead until someone looked. And if that seemed ridiculous, then perhaps so was Copenhagen. By the mid-1930s, the quantum revolution had already changed physics forever. It had given us the strange idea that matter and energy are quantized, that particles behave like waves, and that reality itself might be undefined until observed. But it had also created a philosophical battlefield. Was the quantum world a literal description of reality, or just a mathematical tool? Did observation create reality, or merely reveal it? The cat was Schrödinger's way of throwing that battlefield into the open. It was a challenge, wrapped in fur and placed in a box, daring physicists to explain where the quantum ends and the classical begins. And so, with history swirling behind him, Schrödinger crafted his thought experiment. A single cat imagined, never real, that would carry the weight of one of the deepest questions in science. In the next section, we will open that box in our minds, not to rescue or harm the cat, but to step fully into the paradox. To see how one elegant setup could leave the whole of physics trembling between two worlds. The year is 1935. The air in Vienna is heavy with the memory of coffeehouse debates, the cigarette smoke, and the clink of porcelain cups. At a desk, under the soft glow of a lamp, Erwin Schrödinger sits with a pen in hand. On the page before him, a box begins to take shape, not a box of wood or metal, but one built of thought. Inside this imagined box, he places a cat. The creature is calm, unaware, a heartbeat pulsing quietly in the dark. And beside it, Schrödinger builds a tiny machine, a silent device, waiting for a quantum whisper that may never come. The setup is deceptively simple. It begins with a single radioactive atom unstable, with a 50% chance to decay in 1 hour. Radioactive decay is a quantum process, doesn't obey a fixed schedule. There's no hidden clock ticking inside the atom. Instead, it exists in a superposition, decayed and not decayed until measured. Schrödinger couples this atom to a detector or Geiger counter. If the atom decays, the detector triggers a small hammer. The hammer shatters a glass vial of cyanide gas. The gas fills the box, and the cat stops breathing. If the atom does not decay, the detector stays silent. The glass remains intact, and the cat lives. 1 hour passes. No one looks inside. And according to the Copenhagen interpretation, the atom exists in both states, which means the cat is both alive and dead. It's tempting from a distance to treat Schrödinger's cat as a whimsical riddle, a quirky relic of physics folklore. But for Schrödinger, it was not whimsical at all. It was a deliberate attack. He wanted to show the absurdity of taking quantum mechanics too literally when applied to everyday objects. In the quantum world, superposition is normal. Electrons, photons, and atoms often exist in multiple states at once. But in our world, the world of tables, mountains, and cats, such states collapse long before we notice them. By placing a living creature at the mercy of a quantum event, Schrödinger stretched the Copenhagen interpretation to its breaking point. His message was clear. If your theory makes a cat both alive and dead, perhaps your theory needs help. What makes the cat paradox powerful is the way it links the microscopic and the macroscopic. In quantum mechanics, when two systems interact, their states can become entangled, meaning the condition of one is directly tied to the other no matter how far apart they are. Here, the atom is entangled with the detector. The detector is entangled with the hammer. The hammer is entangled with the vial. The vial is entangled with the cat's heartbeat. The moment you admit the atom can be both decayed and not decayed, you must admit the entire chain exists in a superposition. Hammer swung and unswung. Vial shattered and intact. Cat alive and dead. It's an unbroken bridge from the quantum to the everyday, a bridge that should not exist, and yet does in the math. One of the eerie aspects of the thought experiment is how it forces you to consider the instant before the box is opened. That still, soundless hour where fate is neither sealed nor undecided, but in some sense, both. Our minds are wired to demand clarity. We want the cat to be something even if we don't know what. But Schrödinger's setup suggests that without observation, reality may not commit to a single story. It's like standing at a fork in the road where both paths are taken simultaneously, and only when you step forward does one dissolve. The other, a ghost road, vanishes into the dark. And then, a decision. You lift the lid. Light rushes in. The quantum chain collapses into one reality. In that moment, superposition ends. The atom is either decayed or not. The cat is either breathing or still. This collapse is called wave function collapse, the mathematical reduction of all possible states into the one state we see. In the Copenhagen view, it is the act of measurement that causes this collapse. But this leads to a disquieting question. What counts as a measurement? Does it require a human mind? Could an automated camera do it? If so, when exactly does the quantum haze sharpen into a single reality? Here's where Schrödinger's cat escapes physics and wanders into philosophy. Because the moment you start talking about the role of the observer, you're no longer just doing math. You're touching the edges of consciousness, existence, and the definition of real. Some interpretations argue that the universe itself, through constant interactions and environmental noise, performs the measurement naturally, without a conscious observer. Others cling to the possibility that our awareness plays a special role in shaping reality. In the quiet corners of late-night thought, the cat's box becomes more than a scientific setup. It becomes a stage where physics and metaphysics meet. Many thought experiments fade away with time, replaced by newer, stranger puzzles. But Schrödinger's cat has endured for almost a century. Why? Because it is perfect. Perfectly simple, anyone can picture it. Perfectly absurd, it challenges intuition in a single sentence. Perfectly balanced between the worlds of math, imagination, and philosophy. It is a riddle without an answer, yet one that continues to shape our understanding of the universe. It's worth remembering. No real cat has ever been placed in such a box. Schrödinger himself loved animals and would never harm one for science. The cat exists only in the imagination, but in that space, it has lived and died more times than we can count. It has prowled through textbooks, lectures, films, and late-night arguments. It has become the patron creature of quantum strangeness, and it has reminded us over and over that the way the universe works is not always the way it feels it should. The cat returns to its silent half-life. But the echo of its paradox lingers, pulling us deeper into the quantum twilight zone, a place where particles dance between possibilities, and where the meaning of reality itself becomes slippery. In the world we see, everything appears to be firmly placed in one state or another. A glass sits on the table, or it does not. The sun is above the horizon, or it has dipped below. You are awake or asleep. Reality as we sense it feels binary, clear lines, defined states either or. But deep inside the quantum world, those lines blur. Particles don't seem to care for our human obsession with certainty. Instead, they float in a kind of in-between realm, a twilight space where possibilities overlap, where something can be here and there, this and that all at once. This is the eerie, almost dreamlike concept of superposition. To truly feel how strange superposition is, we have to start with the ordinary. Imagine you're flipping a coin. Before it lands, you might say it's both heads and tails, but in truth, it's only you who doesn't know yet. The coin itself is already tumbling toward one outcome. It will be heads or tails the instant it strikes the table. That's how our everyday classical world works. Even if you can't see the outcome, it's still determined. Reality has already picked a side. Your ignorance doesn't change the fact. In quantum mechanics, however, nature doesn't seem to pick a side until the very moment you look. And in that delay lies a mystery that has puzzled the sharpest minds for a century. We've already met Schrödinger. SCAT in earlier sections, the feline trapped in a box with a device that may or may not release poison. As quantum theory says, until the box is opened, the cat is both alive and dead. In the macroscopic world of living creatures, this is absurd. Cat is a cat. It is breathing, or it is not. But Schrödinger wasn't trying to convince us cats live half-lives in cardboard prisons. He was drawing our attention to the fundamental weirdness of quantum particles. The fact that they can exist in overlapping states until measured. That cat was never meant to be an answer. It was a question in disguise. In quantum mechanics, the state of a particle can be thought of as a wave function, a mathematical shape describing every possible thing it might be. Imagine a shimmering, rippling cloud of possibility. In one place, the probability of finding the particle is high. In another, it's smaller. But until you measure it, the particle exists as all those possibilities at once. It's not indecision. It's not random. It's reality itself holding multiple truths in parallel. To put it differently, a quantum particle in superposition is not 50% here and 50% there. It's 100% in both places, until we force it to choose. Let's go back to our coin flip, but this time, let's enter the quantum realm. You flip a quantum coin, it spins. Time stretches. And instead of falling to heads or tails, the coin becomes something stranger. A perfect blend of both outcomes at the same time. A heads-tails hybrid. Only when you look at the coin does it suddenly and instantly become one thing or the other. This sudden jump is called collapse of the wave function. The coin didn't have a hidden answer waiting for you to find. It became the answer in the very act of you finding it. If the classical world is daytime full of sharp edges, solid objects, and definite events, then the quantum world is twilight. In twilight, shadows are soft, shapes blur. Things exist in an in-between light, where certainty fades and possibility blooms. Superposition is like standing in that dim light. The landscape is there, but indistinct. Until the sun fully rises, until we measure, we live in a realm of maybe. It's here that quantum mechanics forces us to confront a haunting question. Is reality real before we look, or does it crystallize because we look? The most famous proof of superposition comes from the double-slit experiment. Fire tiny particles like electrons at a barrier with two narrow slits. On the other side, a screen records where they land. If we shoot one electron at a time, you might expect it to pass through either one slit or the other. But the pattern on the screen reveals something far stranger. The electrons behave like waves, interfering with themselves, as if each particle traveled through both slits at once. But when we try to observe which slit it goes through, the magic vanishes. The particle chooses one path, and the interference pattern disappears. The act of measuring changes the outcome. The observer is not just a witness, they are part of the story. Superposition is delicate. The moment a quantum system interacts with its environment, a stray photon, a whiff of heat, the overlapping states collapse. This is called decoherence, and it's why you don't see cats, coins, or coffee cups in multiple places at once. On the scale of atoms and photons, it's possible to isolate systems enough to keep superposition alive. But in the warm, noisy world of humans, superposition shatters almost instantly. The universe seems to guard its secrets fiercely, letting us glimpse them only in carefully controlled conditions. While superposition feels like a curiosity, it's more than a thought experiment. It's the foundation of quantum computing machines that use qubits instead of bits. A classical bit is 0 or 1. A quantum bit, in superposition, is both 0 and 1 simultaneously. This allows quantum computers to explore vast combinations in parallel solving. Certain problems unimaginably faster than any classical machine could. In this sense, superposition is not just the twilight zone of physics, it's a doorway to tomorrow's technology. Superposition is unsettling because it challenges our instinct for certainty. What our daily lives, we crave definitive answers. Yes or no. Win or lose. Alive or dead. But the quantum world whispers that reality might be richer, stranger, and less committed than we think. Perhaps this is not just a property of particles, but a hint about the universe itself. That truth may not be a single line, but a tapestry woven from threads of possibility. In that sense, superposition is not a flaw in nature's design. It is the design, as the room is dim. Somewhere in your mind, there's still the faint glow of the cat from the last section curled in its box, existing in that strange both-and state we called superposition. But tonight, something, or rather, someone approaches the box. Not to feed the cat, not to pet it, simply to look. And in that moment, the moment of looking, something irreversible happens. The strange twilight zone of both alive and dead collapses into a single truth. But here's the uncomfortable question. Who or what did the collapse? Was it a human eye, a camera, a measuring device? Or is the universe always watching itself in ways we can barely imagine? This, dear listener, is the observer problem, and it is, in many ways, the heart of quantum physics' biggest mystery. In the everyday world, observation feels simple. You look at your phone, you see the screen. You look at a cup of tea, you see the rising steam. Nothing about these acts feels mysterious. The cup doesn't change because you looked at it. It was hot before you saw it. It will be hot after you turn away. But in the quantum realm, things don't play by these rules. Experiments. When particles are left unmeasured, they behave like waves spread out, capable of existing in multiple states at once. But measure them. Suddenly they pick a definite spot, a definite state. It's as if your act of observing decides reality. The unsettling part. This isn't a metaphor. It's a result we can reproduce in laboratories over and over again. The story of the observer problem almost always leads us to the famous double-slit experiment. Imagine this. We fire a stream of tiny particles, electrons, photons, even atoms at a wall with two narrow slits. Beyond the wall is a screen that catches them. When no one watches the particle's journey, something strange happens. The screen reveals a beautiful interference pattern as if each particle traveled through both slits at once, interfering with itself like a wave. But when we add a detector to see which slit the particle goes through, the pattern changes. The interference vanishes. The particles behave like solid little bullets, choosing one slit or the other. The mere act of measuring, of observing, changes the outcome. The particles seem to know whether or not they are being watched. Here's where things become even stranger. Physicists argue endlessly about what observation really means. Does it require a human mind? So does consciousness shape reality? Or is it enough for a lifeless measuring device to register the result? Some interpretations say the collapse happens the moment the particle interacts with anything capable of recording its state, even an inanimate detector. Others suggest that true collapse only happens when the information enters an observer's awareness. If that second idea is true, then our minds are not just passive witnesses. They are active participants in shaping reality. In the 1970s, physicist John Wheeler proposed a delayed choice experiment. What if you decide whether to measure a particle S-path after it has already passed through the slits? You might expect the particle to have already decided whether it was a wave or a particle before your measurement. But quantum mechanics says otherwise. Your choice made after the fact still determines the outcome. It's as if the universe retroactively rewrites the past to fit the present observation. Time, causality, and common sense all seem negotiable here. One haunting possibility is that the universe exists in a vast superposition of possibilities, until something an observer forces it to commit to one version of events. It's like an infinite stage play where all possible storylines are happening at once, until the spotlight of observation falls and one story becomes real. This idea isn't just physics. It brushes against philosophy, neuroscience, even spirituality. Are we these small creatures on a small planet somehow co-authors of the cosmos simply by looking at it? If the observer problem is true in its deepest sense, it means reality is not as independent as we thought. It doesn't simply exist out there, fully formed, waiting for us to explore. It's made real in the moment of interaction. For some, this is liberating. We are more connected to the universe than we ever imagined. For others, it is terrifying. The ground beneath our feet is less solid than it seems. But you lie here, listening. Imagine that your mind is not separate from the vast machinery of the cosmos. Imagine that every choice to look, every question you dare to ask sends ripples across reality itself. The observer problem may never be fully solved. But in a way, it has already done something remarkable. It has made you part of the equation. Because in the quiet between particles, in the shimmer between possibility and fact, someone has to be watching. And tonight, that someone is you. In the quiet corridors of scientific history, there comes a moment when an idea, once trapped in the amber of imagination, begins to wriggle toward reality. Schrödinger's cat was never meant to be a real creature. It was a thought experiment, a parable wrapped in fur and paradox, meant to expose the absurdity lurking inside quantum theory. Yet over time, physicists curious, stubborn, and slightly mischievous began asking themselves, what if we could really put the cat in the box? Not a living cat, of course, but something that could, in some deep and quantum sense, be both alive and dead, both here and there at the same time. And so, like dreamers turning sketches into blueprints, they began to build the boxes. In the early decades after Schrödinger's 1935 proposal, the cat lived solely in the minds of physicists. They could debate its fate over coffee and chalkboards, but no one had the tools to test it. Quantum effects seemed locked in the tiny realm of atoms and electrons, far smaller than a cat, or even a single cell. But as technology crept forward, so too did the ambition to push quantum strangeness upward in scale. Lasers were invented. Vacuum chambers became cleaner. Magnetic fields could be controlled with breathtaking precision. Suddenly, it was no longer a question of if quantum superposition could be tested with larger objects. It was a matter of when. The first candidates for these quantum cats were not furry at all. They were ions trapped in electromagnetic fields, cooled to a fraction above absolute zero. These ions could be coaxed into two different energy states simultaneously, a faint echo of the cat's dual life and death. Later came superconducting circuits, where loops of current could flow clockwise and counterclockwise at the same time. Surreal state that would make a classical electrician shake their head in disbelief. One of the great pioneers in this field was David Wineland. His work in ion trapping eventually earned a Nobel Prize. Picture an ion just a single atom, stripped of an electron suspended in a cage of electric and magnetic fields. Here, in a vacuum better than outer space, scientists can whisper to the ion with the soft light of a laser, nudging it into superposition. In such an experiment, the alive and dead states of Schrödinger's cat are replaced by two distinct states of the ion. Different energy levels, or even to separate positions in space. The ion exists in both until an observation collapses the wave function into one outcome. For a moment, the metaphorical cat stretches its paws between two universes. And this was no longer philosophical musing at, was data. The laser pulses, the interference patterns, the delicate control over decoherence, all of it could be measured, plotted, and repeated. The line between the imaginary and the real was beginning to blur. While ions floated in their magnetic cages, another breed of experiment was being born in the chilled stillness of superconducting circuits. Here, electrons flow without resistance, weaving around loops and states that defy classical logic. These loops can exist in a superposition of current flowing clockwise and counterclockwise. At the same time, an almost perfect mechanical analog of the cat being both alive and dead. The beauty of superconducting cats is that they can be integrated into quantum computers. Each qubit in such a system can hold a superposition, allowing for the eerie parallelism that fuels quantum computation. In a sense, quantum engineers had not only let the cat out of the box, they'd built entire cat colonies, each purring in many states at once. Then there are the Rydberg atoms, giant atoms puffed up like cosmic balloons, their electrons orbiting far from the nucleus. These atoms are so large in atomic terms that they become exquisitely sensitive to electric and magnetic fields. Physicists can place them into fragile superpositions, coaxing them into delicate dances between states. What's remarkable is how long these superpositions can last, even in the noisy environment of a lab. It's as if the cat, once released from the thought experiment, has learned to linger on the threshold between life and death longer than Schrödinger ever dared imagine. Not all cats have mass. Some are made of pure light. In the field of quantum optics, scientists create states of light that are superpositions of distinct phases or polarizations, so-called Schrödinger S-cat states of photons. These experiments push the metaphor to its limit. Instead of a creature in a box, we have packets of light in quantum limbo. It's neither one thing nor the other, until a detector seals their fate. One of the most elegant advances in this field is the development of weak measurements, ways of gathering information without fully collapsing a quantum state. Imagine opening the cat's box just a crack. Enough to hear a faint purr, but not enough to disturb whatever strange coexistence it inhabits. Weak measurements allow physicists to probe the nature of quantum systems with unprecedented subtlety. We can, in a way, watch the cat without sentencing it to one fate or another. This is not just a technical triumph, it is a philosophical revelation. It suggests that the boundary between knowing and not knowing is not a cliff but a slope, and that reality may yield its secrets in shades rather than absolutes. As experiments have scaled up, the central mystery remains. Why does quantum weirdness vanish at the macroscopic level? If ions, photons, and superconducting loops can be in superposition, why not cats, chairs, or planets? Some suspect that decoherence, the inevitable entanglement of a system with its environment, acts as a relentless spoiler, collapsing superpositions before they can grow to classical scales. Others wonder if there's a deeper principle at work, something still hidden in the mathematics. It's a question that stretches beyond the lab, brushing against the fabric of the cosmos itself. If the universe began in a quantum stadia, cosmic cats, both alive and dead, then the act of observation may be woven into the story of existence from the very first instant. Today, Schrödinger's cat lives in more places than anyone could have predicted. It resides in the supercooled chips of quantum computers, in the flicker of entangled photons, in the magnetic hum of ion traps. It even prowls through biology as researchers explore whether quantum effects play a role in processes like photosynthesis or bird navigation. The cat has escaped its original box, but it has not escaped the question it was meant to raise. What is reality before we look at it? In chasing an answer, we've built machines that can cradle the impossible, if only for a heartbeat. And perhaps that is the truest escape, when a metaphor becomes an experiment, and an experiment becomes a doorway into worlds we once thought belonged only to imagination. There are nights when you lie awake in bed, staring at the ceiling, and wonder what if every choice you could have made was made. What if every yes and no, every step forward and step back, every unopened door and every path you never took, still exists somewhere, unfolding in its own quiet, parallel rhythm. And in that somewhere, the cat in Schrödinger's box is not either alive or dead. It is alive and dead. It is purring in one world and still in the other. Both outcomes, both stories, both realities are real. This is the promise and the problem of the many worlds interpretation. The idea of many worlds came not from a poet or a science fiction author, but from a graduate student. In 1957, Hugh Everett III, just 27 years old, dared to suggest something radical. Quantum events don't collapse into one outcome. Instead, every possible outcome happens, each in its own branch of the universe. Think of the universe not as a single line stretching from the Big Bang to now, but as a constantly branching tree. Every interaction, every quantum event, is a fork in the path. A photon can be here or there, so the universe splits effortlessly into a version where it's here and another where it's there. Coin toss doesn't land on heads or tails. It lands on both in different universes. In Everett's view, Schrödinger's cat does not occupy some vague, ghostly blur of alive and dead until we open the box. Instead, the moment the mechanism triggers, the universe splits. One branch contains you opening a box to find a living cat, whiskers twitching in relief. The other branch contains you opening a box to find stillness. You exist in both branches, but in each one, you only remember one outcome. In the Copenhagen interpretation, measurement is like a divine finger pressing the universe into one state. In many worlds, there is no such collapse. There is no privileged observer. Reality doesn't choose. It proliferates. It's a strange kind of economy where the currency is universal and the market is booming endlessly. Every quantum event spawns another. Your every blink, every neuron firing, every molecule jostling in your coffee cup, each has a tiny probability of being different. And each difference is another branch. The universe becomes not a single stage, but an infinite theater, performing every play, every improvisation, every possible act forever. Let's take you as an example. Right now, you are here, listening to my voice. But in another branch, You paused this a minute ago to make tea. In another, you never found this video. In another, you decided physics wasn't worth your time and you're watching a cooking show instead. And in countless others, you don't exist at all. This isn't science fiction, according to Everett. It is the mathematics of the wave function applied without the special rule of collapse. The equation that describes the quantum world doesn't need a mysterious observer to force a choice. It simply evolves into everything. Return to the cat. In many worlds, there is no moment where we peak and decide the cat's fate. The cat's fate is decided, but in both ways at once. One universe contains the living cat, another, the dead one. Both are as real as the universe you are in now. There is no master reality, no central thread, just an endless, equally valid tangle. To visualize it, imagine standing in a vast field at night. Around you, in every direction, countless fireflies flicker on and off. Each blink is a branch of an entire universe igniting into existence, then continuing on its own path forever. From where you stand, you only see your own patch of light. But from above, from a God's eye view, the whole field is alive. But many worlds comes with a cost. It is not a comforting theory, because if every possibility exists, then so do all the tragedies, all the mistakes, all the horrors we wish never happened. For every universe where you saved the cat, there is one where you didn't. For every universe where peace prevails, there is one where war never ends. Everett himself admitted he didn't like the philosophical baggage. It removes the uniqueness of our choices in some sense. Everything that can happen does happen. But it also removes the mystery of collapse. The mathematics of quantum mechanics works perfectly. Without special exceptions for observers, it is both elegant and heavy. And here is the strangest part. If many worlds is correct, then Schrödinger's cat is still alive somewhere, still dead somewhere else. In some universes, it was never put in the box at all. In others, you never heard its story. The thought experiment becomes a living thing, not frozen in textbooks, but growing endlessly into the infinite fractal of reality. You might find this dizzying or liberating, or perhaps both. Because if every possible version of you exists, then somewhere, in some branch, you are doing exactly what you most wish you could do. And somewhere else, you are avoiding your deepest fear. The cat has not just escaped the box, it has escaped the very idea of a single fixed fate. And in that, perhaps, lies the real lesson. We may live in one branch, with one set of memories, but the universe's imagination is endless. And just maybe, you are too. If the laws of quantum physics could speak, they might not talk to us in the language of equations or graphs, but in riddles. Riddles woven from light and shadow, possibility and paradox. And humanity, even the curious child, has spent more than a century leaning in, listening, trying to guess the punchline. We live in a world that feels solid, dependable, and fixed. The desk you're sitting at, the phone in your hand, the walls around you seem so certain. But quantum physics tells us this certainty is an illusion, a kind of narrative our minds have written to make sense of something far stranger. Beneath the comforting stage set of reality lies a restless play of probabilities. An orchestra of particles flickering between is and is not. And it is here, in this shimmering in-between, that human imagination steps in. When quantum mechanics first emerged in the early 20th century, it wasn't just a revolution in physics, it was an earthquake in thought. Scientists weren't used to the universe being this mischievous. They had been trained to expect order, precision, and clear causes leading to clear effects. And yet there was a theory saying that a single electron could be in multiple places at once, that outcomes couldn't be predicted with certainty, only with probability, and that observation itself seemed to shape the very thing being observed. This wasn't just a problem for the physicists' chalkboards, it was a problem for their imaginations. How do you picture a cat that is both alive and dead? How do you imagine a world where cause and effect might be connected not in a straight line but in a shimmering web of possibilities? The human brain is built to tell stories, and quantum physics seemed to demand a new kind of storytelling, one that didn't require choosing just one ending. The strange beauty of quantum theory began to spill beyond the laboratory and into culture. Science fiction writers, poets and philosophers saw in it a perfect metaphor for the uncertainties of human life. In literature, the idea of branching realities, parallel universes where different versions of us live out different choices, became irresistible. Novels like The Man in the High Castle, films like Everything Everywhere All at Once, and countless short stories have borrowed quantum mechanics as their stage. In these stories, the rules are not fixed, and reality bends to accommodate infinite outcomes. Artists painted overlapping images, blurred forms, and fractured perspectives to suggest the coexistence of possibilities. Playwrights imagined characters split between timelines. And in music, composers began experimenting with chance-based compositions, where each performance could be subtly different, echoing the probabilistic heart of quantum theory. Science was never just science. It became a mythos, a source of metaphors for love, memory, and the human condition. One of the most tantalizing things about quantum reality is that we can never directly see it as it is. Our instruments can measure, our equations can predict, but the reality itself, the dance of possibilities before they collapse, remains hidden behind a curtain. And this is where imagination becomes not just decoration, but necessity. Just as ancient humans looked at the stars and imagined gods, animals, and heroes painted across the night sky, modern humans look into the probabilistic haze of the quantum world and imagine what could be happening there. For scientists, this is not mere indulgence. In fact, visualization is one of the most important tools in theoretical physics. When Richard Feynman wanted to understand particle interactions, he drew diagrams that looked almost like constellations. When Schrödinger wanted to explain quantum superposition, he didn't produce a thicker textbook. He told a story about a cat. Quantum mechanics does not just describe the universe. It reflects the mind that tries to understand it. The uncertainty principle. The idea that you cannot know both a particle's position and momentum precisely at the same time has often been taken as a metaphor for life itself. In life, as in physics, some things are mutually exclusive. To hold on to one path too tightly may mean letting another slip away. To measure one possibility too sharply may mean blurring all the others. In this way, the quantum world becomes a mirror, showing us how our choices and perceptions shape the realities we experience. The observer effect in physics has a poetic cousin in psychology. We change the world simply by being in it. When we close our eyes at night, our minds slip into a space that is neither fully real nor fully imaginary, the dream world. In dreams, logic softens, time bends, and the impossible feels ordinary. Quantum mechanics, with its superpositions and entanglements, often feels like that same dream logic leaking into waking life. It's no wonder, then, that the quantum world feels so natural to storytellers. It offers a scientific justification for the dreamer's intuition, that the world is not as rigid as it seems. In the quantum picture, the walls between what is and what might be are paper-thin. Today, real quantum experiments, from superconducting qubits to entangled photons, confirm that the universe truly behaves in these bizarre ways. But for most of us, the equations are secondary. What we take home from quantum mechanics is the feeling it gives us, that reality is bigger, stranger, and more full of possibility than we had ever dared imagine. And for those listening late at night, lying in the quiet dark, that feeling is a kind of comfort. If the universe itself can hold contradictions, if it can be both one way and another, then perhaps so can we. Perhaps our choices don't close every door. Perhaps there are always more paths than we think. The cat in Schrödinger's box was never just a cat. It was the embodiment of human imagination, curling up in the warm uncertainty between knowing and not knowing. In the end, quantum reality is not a cold, alien world. It is a landscape we have been walking in all along. Whenever we dream, whenever we wonder, whenever we imagine that more is possible than what we can see, the cat, as strange as it was never the end of the story. Schrödinger's thought experiment was a mirror held up to a puzzle in nature, a way of saying, look, here's the paradox. But science is a restless traveler. Once it has looked into one box, it searches for another. And in the centuries since that imagined feline sat in the half-light between life and death, quantum physics has leaped far beyond the playful cruelty of that metaphor. We now stand at the edges of entirely new realms, so strange that even the cat with its dual fate might seem simple by comparison. This is where quantum mechanics spills into technology, computation, communication, and even the fabric of space-time itself. For decades, quantum mechanics was a theory of limits, a set of rules describing the tiny, strange motions of particles, but too fragile and impractical to touch the real world. The cat was a thought experiment precisely because no one could imagine superpositions of life and death existing in anything bigger than an atom. Yet here we are in the 21st century, learning not just to imagine, but to control quantum states and objects made of trillions of atoms. We have coaxed photons into delicate dances across thousands of kilometers without losing their quantum link, a feat Einstein once dismissed as spooky action at a distance. We have built machines that can hold superpositions not for fractions of a second, but for long enough to perform calculations impossible for any classical computer on Earth. The cat has slipped out of its imagined box and found itself reborn as qubits, the fundamental units of quantum computation. In the classical world, computers think in bits, 0 south or 1 south, open or closed, on or off. But in the quantum world, a qubit can be both 0 and 1 at the same time, in superposition. And the magic multiplies when qubits become entangled. Their states lock together so that knowing one instantly tells you about the other, no matter the distance between them. A network of entangled qubits can explore vast landscapes of possibilities all at once, performing certain types of calculations not in centuries, but in seconds. This is not just a faster calculator. It is a fundamentally different way of processing reality. Quantum computing promises breakthroughs in materials science, cryptography, pharmaceuticals, and even the modeling of the quantum world itself. In some poetic way, we are using quantum mechanics to understand quantum mechanics, the cat helping us solve its own riddle. There is another frontier: quantum communication. Classical signals, radio, light, electrical pulses can be intercepted or copied, but quantum signals, they are protected by the very laws of physics. Measure them, and you change them. Eavesdrop, and you leave a detectable scar in the data. This has given rise to quantum key distribution, a method of secure communication where two parties can exchange cryptographic keys with absolute certainty that no one is listening. This technology is already being tested in satellites, fiber optic networks, experimental systems that hint at a coming quantum internet, a global web where information travels as entangled states. Immune to conventional hacking. Cat's paradox was about observation, how the act of measurement changes the thing being measured. Physicists have found ways to use that same fragility to our advantage. Quantum sensors can detect the tiniest shifts in gravity, magnetic fields, or time itself with astonishing precision. These devices could map underground structures without digging, detect gravitational waves from colliding black holes, or create clocks so accurate they would lose less than a second over the entire lifetime of the universe. The box, it seems, has been transformed into a laboratory, and the cat into a precision instrument. Perhaps the most surprising new frontier is biology. For years, quantum effects were thought to vanish in warm, wet environments like the human body. Yet evidence now suggests that certain biological processes, photosynthesis in plants, navigation in migratory birds, even aspects of our sense of smell may rely on quantum phenomena. If this is true, the cat in the box is not just a metaphor. It might be a reflection of nature's own hidden machinery, whispering through the cells of every living thing. There is one frontier that towers above all others: the unification of quantum mechanics with general relativity. Gravity, Einstein's great legacy, bends space and time on a cosmic scale, while quantum mechanics governs the subatomic. But the two theories are stubbornly incompatible. Physicists dream of a quantum theory of gravity, a framework that explains black holes, the birth of the universe, and the strange foam-like structure of space-time at the smallest scales. Here, the cat becomes a cosmic creature, symbol of the ultimate mystery: how the universe holds both the very large and the very small in one coherent reality. From string theory to loop quantum gravity, from holographic principles to wormhole simulations, we are still building the box for this experiment. And perhaps like Schrödinger's cat, the answer will only exist when we dare to look, In the end, the strange thing about the new frontiers in quantum physics is that the more we learn, the stranger it gets. We have gone from imagining a cat that is both alive and dead to building machines that harness that duality. We have turned paradox into power, uncertainty into understanding. Yet every breakthrough opens 100 new doors. The universe seems to whisper, "You have not reached the end of the box, only another layer of it." And perhaps that is the true legacy of the cat, not the thought experiment itself, but the mindset it created. A willingness to believe that the world might be far stranger, far richer, and far more beautiful than our first glance would suggest. It begins with a box that is, in truth, a doorway. Inside, a cat that is neither fully alive nor fully gone, cat that is both and neither. It is the image we have carried with us through this journey, or symbol, our paradox, our key. But as we close this series, it becomes clear. The cat was never really about the cat. It was never just about quantum mechanics or even about physics. It was about us. About this strange, insistent hunger that lives in the human mind, the hunger to ask why, even when we know the answer may not come. For thousands of years, we have stared at the night sky and seen not only stars, but stories. We have asked questions about the shapes of constellations, the distances between planets, the way the cosmos seems both infinite and intimate. When we learned to split atoms and peer into the quantum realm, our questions did not stop. They simply grew stranger. We began to ask, what is reality? Does the universe choose a single path, or does it split into many? Is an unmeasured particle everywhere, or nowhere at all? And in the quiet between those questions, another one forms. Why does it matter to us so deeply? The cat in the box is our reminder that the universe plays by rules that often defy our intuition. In our everyday lives, we think of objects as having definite positions, definite states. A cup is on the table, or it isn't. A light is on, or it's off. A cat is alive, or it is gone. Yet quantum physics whispers. The truth is more fluid. Till an interaction happens subtle, the universe is asked. A question reality itself hovers in a strange in-between. This in-between is not just a property of particles. It is a reflection of our place in the cosmos. We live suspended between knowing and not knowing, between what is and what could be. We exist in a state of curiosity, our minds forever entangled with mysteries we may never solve. The cosmos, vast and ancient, does not need us. It spins its galaxies, it burns its stars, it collapses its suns into black holes without our permission or understanding. And yet here we are, tiny sparks of awareness, looking back at it, asking questions, daring to imagine. We are, in a sense, the universe observing itself. The cat and the cosmos are part of the same story, and we are both the observers and the observed. When Schrödinger first imagined his cat, it was a thought experiment meant to challenge the strange implications of quantum theory. But over time, it became something more, a cultural icon, a bridge between science and philosophy, a way for anyone, physicist or not, to touch the edges of a reality stranger than fiction. It invited us into the twilight zone where the limits of human logic meet the wildness of nature's laws. And here's the most important thing. The questions never end. Once we understand superposition, we wonder about entanglement. Once we imagine many worlds, we wonder about their connections. Once we consider the role of observation, we ask who or what might be observing us. The cat reminds us that every answer contains another question. Every conclusion is really an opening act for the next chapter of curiosity. And perhaps that is the point, not to reach an ending, but to remain in the dance between knowing and mystery. Some say the universe is like a book. But I think it is more like a conversation. Every experiment, every discovery is a reply to a question we asked, and in the reply hidden between the lines is another question waiting to be spoken. We are not reading a story that has already been written. We're co-authoring it, line by line, with reality itself. Tonight, somewhere, a scientist is running an experiment to test the boundaries of quantum theory. Somewhere else, a child is lying awake, staring at the ceiling, wondering about the stars.
Ow.
In both cases, the impulse is the same.
Ow.
It is the same impulse that made our ancestors paint the walls of caves.
Ow.
build telescopes, split atoms, and imagine boxes containing impossible cats. It is the same impulse that will carry us beyond the cat, beyond the box, beyond even quantum physics, to the next frontier we cannot yet name. And when we get there, we will do what we have always done. We will keep asking. Because the cat was never really about the answer. It was about the wonder that made us open the box in the first place. So as we close this journey, remember, the cosmos is vast, and the questions are endless. But so is our capacity to imagine, to wonder, to seek. And in that endless seeking, we are perhaps as close to the heart of the universe as we will ever be. This is the Sleep Scientist. Thank you for staying awake or drifting gently to sleep with me tonight. If you've enjoyed this journey, I invite you to join me again as we open new boxes, chase new questions, and wander together into the unknown. Until then, sweet dreams and keep wondering.